Welcome to your AP Statistics Chapter 20, video number 1. Today we're going to talk about testing hypotheses about proportions. Hypotheses are a working model that we adopt temporarily. Our starting hypothesis is called the null hypothesis. The null hypothesis that we denote by H0 specifies a population model parameter of interest and proposes a value for that parameter. Remember, we get a statistic from our data set, from our sample, that is an estimate of the parameter. So here we're proposing a value for that parameter. We usually write down the null hypothesis in the form H0 and then colon parameter equals hypothesized value. The alternative hypothesis, which we denote by HA, contains the values of the parameter that we consider plausible if we reject the null hypothesis. The null hypothesis specifies a population model parameter of interest and proposes a value for that parameter. We might have, for example, H0 p equals 0.20 as in the chapter example. We want to compare our data to what we would expect given that the null hypothesis is true. So we would expect to end up with a sample proportion somewhere in the neighborhood of 0.20, not exactly the same necessarily, but somewhere close. We can make this comparison by finding out how many standard deviations away from the proposed value we are. We then ask how likely it is to get the results like we did if the null hypothesis were true. If the true population proportion is really just 0.2, how likely is it that we get the proportion we observed in our sample? A trial is a hypothesis test. Think about the logic of jury trials here in the United States. To prove someone is guilty, we start by assuming they are innocent. We retain the hypothesis until the facts make it unlikely beyond reasonable doubt. Then and only then, we reject the hypothesis of innocence and declare the person guilty. The same logic used in jury trials is used in statistical tests of hypotheses. We begin by assuming that a hypothesis is true. Next, we consider whether the data are consistent with the hypothesis. If they are, all we can do is retain the hypothesis we started with. If they are not, then like a jury, we ask whether they are unlikely beyond a reasonable doubt. The statistical twist is that we can quantify our level of doubt. We can use the model proposed by our hypothesis to calculate the probability that the event we've witnessed can happen. That's just the probability we're looking for. It quantifies exactly how surprised we are to see our results. This probability is called a p-value. Notice it's a capital P to kind of help you tell the difference between the p-value and the value of p, the population proportion. When the data are consistent with the model from the null hypothesis, the p-value is high, and we are unable to reject the null hypothesis. So, if something happens 85% of the time, nobody's surprised. So a large p-value, if the p-value is very, relatively speaking, large, then you're not surprised by it. The data are consistent with the null. And so in that case, we have to retain the null hypothesis we started with. We can't claim to have proved it. Instead, we fail to reject the null hypothesis when the data are consistent with the null hypothesis model and in line with what we would expect from natural sampling variability. If the p-value is low enough, we'll reject the null hypothesis since what we observed would be very unlikely were the null model true. So if we have a really small p-value, it's surprising that it happened, and so we reject the null. What do we do with the quote-unquote innocent defendant? If the evidence is not strong enough to reject the presumption of innocent, then the jury returns with a verdict of not guilty. The jury does not say that the defendant is innocent. All it says is that there is not enough evidence to convict, to reject innocence. The defendant may in fact be innocent, but the jury has no way to be sure. The defendant may in fact be guilty. It's just that the evidence provided wasn't enough to make the jury go, oh yeah, beyond a reasonable doubt, this person is guilty. Okay, the evidence presented was consistent with somebody being innocent. Said statistically, we will fail to reject the null hypothesis. We never declare the null hypothesis to be true. And we don't say we've proven anything because we simply do not know whether it's true or not. Sometimes in this case, we say that the null hypothesis has been retained. I strongly suggest that you get used to saying we fail to reject the null hypothesis because the data are consistent with the null hypothesis, not the retained part, because some statistics professors really have a cow. They don't like that language. So you can say it, but just know some people feel like it blurs the lines too much. In a trial, the burden of proof is on the prosecution. Okay, the prosecuting attorney has to present enough evidence to convince the jury beyond a reasonable doubt that the defendant is guilty. In a hypothesis test, the burden of the proof is on the unusual claim, the alternative hypothesis. The null hypothesis is the ordinary state of affairs, so it's the alternative to the null hypothesis that we consider unusual and for which we must marshal evidence. It's also what we tend to have a hunch is true. Just like a person's not brought to trial unless the prosecutor thinks that they're guilty. Prosecutors in general don't bring innocent people to trial. It's a waste of time, money, and it's, not a very nice thing to do. You're not going to conduct a hypothesis test when that you don't think the alternative is actually the true state of affairs. Okay, but the assumption is that the null hypothesis is true, and you garner evidence that your alternative is true. There are 4 basic parts of a hypothesis test: hypotheses, model, mechanics, and conclusion. Let's look at these parts in detail. Hypotheses. You always list your null first and then your alternative. The null hypothesis. To perform a hypothesis test, we must first translate our question of interest into a statement about model parameters. In general, we have null hypothesis, H naught, parameter equals hypothesized value. For the alternative hypothesis, HA, this is going to contain the values of the parameter we consider plausible when we reject the null. The second thing is the model. To plan a statistical hypothesis test, specify the model you would use to test the null hypothesis and the parameter of interest. For instance, the first one we're going to learn about is we are going to learn about one proportion z-tests. So you want to mention that. Stating the mean and the standard deviation would be great too. All models require assumptions. So state the assumptions and check any corresponding conditions. That's going to be extremely important if you want to get good grades on the free response of the AP exam. Your model step should end with the statement such as, because the conditions are satisfied, I can model the sampling distribution of the proportion with the normal model. Watch out though, it might be the case that your model step ends with, because the conditions are not satisfied, I can't proceed with the test. If that's the case, stop and reconsider. Each test we discuss in the book has a name that you should include in your report. The test about proportions is called a one proportion z-test, just like I said. And on the AP exam, typically you get credit for identifying a test either by name, one proportion z-test, or by having all the formulas like for z. And so that's going to be a little bit more involved to remember the formulas. It's good to remember them, but you can use your calculator to give you your corresponding z value without having to memorize the formula, but you can't get to the correct test in your calculator without knowing what kind of test you have to use. So the most efficient thing to do is to name your tests, because you're going to have to know the name of the test you want to use to go to the right place in the calculator anyway. So this is extremely important. You always want to declare what test you're doing. So right now that's easy. It's one proportion z-test. The conditions for one proportion z-test are the same as for one proportion z-interval. So we know those conditions. We test the hypothesis H naught, P equals P naught. Okay, P naught is the hypothesized value. Earlier we talked about it might be 0.2. That would be the P naught for that situation. Using the statistic Z equals P hat minus P naught over the standard deviation of P hat, where the standard deviation of P hat is the square root of P naught times Q naught over N. Now, remember earlier I said on the AP exam when you're doing a hypothesis test, one of the things they look for is that you've declared which kind of test it is, either by name or by formula for Z. Well, it's a lot easier, I think, to go ahead and write down the name than to remember to write down the formula, especially because the calculator you're going to find calculates Z for you. So this would be extra work. This would just be declaring where you're looking in your calculator, really. When the conditions are met and the null hypothesis is true, the statistic follows the standard normal model. So we can use that model to obtain a p-value because we can find areas under that normal curve, standard normal curve, and they give us the probabilities we're looking for. Under mechanics, we place the actual calculation of our test statistic from the data, or we report it. Different tests will have different formulas and different test statistics, G versus T versus chi-squared, and we'll get into the other ones later. Usually the mechanics are handled by statistics program or calculator, yay, but it's good to know the formulas. And it is good to know the formulas. Remember, time is of essence on the AP exam, so it's going to be very important that you can actually put this stuff into your CAS and let it do the number crunching for you as quickly as possible. The ultimate goal of the calculation is to obtain a p-value. Okay, this is extremely important that you know this. Okay, so really focus in if your mind has been wandering. The p-value is the probability that the observed statistic value, or an even more extreme value, could occur if the null hypothesis were correct. So it's the probability that we would get a result at least as extreme as the one we did if the null hypothesis were true. If the p-value is small enough, we'll reject the null hypothesis, okay? Because that means it's unlikely. If it's a small p-value, that means it's a very small probability that we would get a result at least as extreme as the one we did if the null hypothesis were true. It's surprising, so that's going to be enough evidence to reject the null hypothesis. Please note that the p-value is a conditional probability. It's the probability that the observed results could have happened if the null hypothesis were true, and so it's critical that you remember that last part. All right, the last part of our hypothesis test is the conclusion. The conclusion in a hypothesis test is always a statement about the null hypothesis, okay? Always about the null. We either reject it or we fail to reject it, okay? So the conclusion must state either that we reject or that we fail to reject the null hypothesis. And as always, the conclusion should be stated in context. Your conclusion about the null hypothesis will not typically be the end of the testing procedure. Often there are actions to take or policies to change. The big so what? Why did you even care? Why do the test in the first place? Why think about it? Why bother coming up with an alternative? Well, there's usually a really good practical reason for it. All right, alternatives. There are three possible alternative hypotheses. Either our alternative is that we believe the parameter is less than the hypothesized value, or we believe that the parameter is just not equal to the hypothesized value, or we believe the parameter is greater than the hypothesized value. Okay, if we have no good reason to think of a direction either less than or greater than, we go with the not equal to. But sometimes we do ahead of time think, oh no, the parameter really is less than what has been assumed to be true forever, or the parameter is now greater than what's been assumed to be true. So you really have to think about what the alternative is going to be. For you guys, it's going to be a matter of reading very closely to see what's presented in the problem. Okay. The alternative where the parameter is not equal to the value is known as a two-sided alternative because we are equally interested in deviations on either side of the null hypothesis value. For two-sided alternatives, the p-value is the probability of deviating in either direction from the null hypothesis value. Okay, so what we observe will be in one tail or the other, but we have to consider the probability that we would have gotten a similar result but on the opposite side, because it considers both directions. Your calculator will do that for you automatically. The other two hypotheses are called one-sided alternatives. A one-sided alternative focuses on deviations from the null hypothesis in only one direction. Thus, the p-value for our one-sided alternatives is the probability of deviating only in one direction of the alternative away from the null hypothesis value. So if we think our proportion is really less than 0.2, we would only be interested in the area to the left of the observed value. So in this case, if we observe 0.17, the probability of getting a sample proportion of 0.17 or smaller is 0.069. Okay. Previously, if we were interested in either direction, even if we got 0.17, that's 3/100ths smaller than 0.2, and so we have to consider 3/100ths larger than 0.2 also, and consider both tails. So it's going to have a probability of 0.069 plus 0.069. P-values and decisions. What to tell about a hypothesis test? How small should the p-value be in order for you to reject the null hypothesis? It turns out that our decision criterion is context dependent. When you're screening for a disease and want to be sure we treat all those who are sick, we may be willing to reject the null hypothesis of no disease with a fairly large p-value, say 0.1. A long-standing hypothesis believed by many to be true needs stronger evidence and a correspondingly small p-value to reject it, so 0.05 or maybe even 0.01. Another factor in choosing the p-value is the importance of the issue being tested. Your conclusion about any null hypothesis should be accompanied by the p-value of the test. If possible, it should also include a confidence interval for the parameter of interest. Don't just declare the null hypothesis rejected or not rejected. Report the p-value to show the strength of the evidence against the hypothesis, and this will let each reader decide whether or not to reject the null hypothesis. Okay, well that's going to be it for video 1, and we're going to come back and talk about things that can go wrong and look at some examples for video 2. I'll see you in a few.